Welcome to TechGen Manufacturing. Today, I will personally guide you through a monumental subterranean engineering marvel. At 350 meters below the surface, a $40 billion underground megaport is being built. The massive tectonic pressure reaching 8.5 megapascals represents our very first extreme physical barrier. Every single square meter of this cavern must withstand thousands of tons of shifting lithospheric weight. Our primary engineering goal is constructing a terminal capable of processing millions of passengers in total isolation. Look closely at the structural design. The immense cavern stretches 15 stories high beneath solid granite layers. Traditional architecture fails completely here. We must utilize specialized heavy titanium alloy lining plates for reinforcement. The primary operational threat under this closed environment is the accumulation of fine, destructive, abrasive granite dust. If microscopic dust particles infiltrate the advanced avionics systems, the aircraft propulsion engines will fail instantly. To counter this critical risk, we engineered the heart of the system, a positive pressure clean room. This massive isolation structure completely encloses the boarding gates and passenger terminal corridors deep underground. The walls are constructed from high-strength ivory white carbon fiber composite panels to maximize structural stability. Embedded deep within these composite structures are military-grade HEPA filter grids to capture every microparticle. 14 million cubic meters of air must be continuously processed and circulated through these filters every hour. This relentless atmospheric circulation maintains a stable positive pressure environment, blocking any external geological debris. Let us examine the logistical framework required to transport equipment down to this terrifying depth. Standard industrial elevator systems are completely inadequate for moving massive structural components needed here. To bypass this limitation, we had to excavate 3 independent giant vertical drop shafts. Each shaft has a perfectly machined diameter of 25 meters, piercing straight through rock layers.
The scale of this operation is truly staggering. These cables alone weigh over 50 tons and are essential for powering the deep shaft operations below.
Above me, a colossal prefabricated steel girder weighing 450 tons is slowly descending. The entire structural weight is supported by an advanced synchronous 4-point hydraulic hoist system. Digital sensors track the load balance continuously, maintaining a leveling tolerance below 1 single millimeter. Any sudden imbalance during this vertical descent would cause a catastrophic structural impact against walls. Once the giant girders reach the bottom, specialized heavy-duty multi-axle transporters receive the load. These low-profile mechanical movers slowly navigate the narrow, dark tunnels leading to the terminal core. Simultaneously, the structural integrity of the raw excavated tunnel walls must be reinforced immediately. We utilize an automated shotcrete method using robotic arms to spray advanced polymer concrete blends. This specialized high-density material forms an impenetrable shield against immense high-pressure underground water currents. Without this critical polymer barrier, groundwater would breach the structural foundation within 48 hours. With the geostructural foundation secured, we advance to the critical aerodynamic mitigation phase of our terminal design. When commercial aircraft move inside enclosed underground tunnels, they create immense piston effects and air displacement. This massive compressed air mass ahead of the aircraft generates extreme friction and destructive turbulence barriers. To resolve this physical barrier, we engineered specialized shockwave relief chambers along the primary runway tunnel. These massive bypass caverns absorb the extreme pressure waves, redirecting air currents away from the path. Each shockwave relief chamber requires thick, vibration-dampening reinforced concrete buffers capable of structural deflection. We must continuously monitor the structural response of these buffers using long-gauge fiber optic sensors. These highly sensitive optical lines detect microstrains within the concrete structure at a picometer scale. Next, look at the integration of the main underground terminal electrical power distribution infrastructure system. A project of this extreme magnitude demands an independent dual-feed 400 kilovolt subterranean substation. Heavy-duty sulfur hexafluoride gas-insulated switchgear units are assembled to guarantee complete fire and explosion safety. The massive electrical cables are routed through dedicated concrete trenches equipped with automated liquid nitrogen cooling. This intense cooling process prevents dangerous thermal accumulation caused by continuous heavy, high-voltage electrical transmission. Any sudden drop in power grid stability would instantly paralyze the critical life support and ventilation. Therefore, a massive backup battery energy storage matrix is installed to provide instantaneous auxiliary power. Let us shift our focus to the high vacuum infrastructure developed for the high-speed baggage logistics system. Moving baggage between 5 subterranean terminal floors at extreme depth requires a complete pneumatic revolution. We built a sprawling network of sealed stainless steel tubes traversing the primary structural columns. Heavy-duty industrial vacuum pumps reduce internal tube pressure to achieve near-zero air resistance coefficients. Automated magnetic levitation capsules transport luggage through this vacuum matrix at 30 meters per second. To guarantee structural absolute safety, every single tube junction undergoes extreme structural stress testing. Mechanical actuators violently flex and compress the steel joints millions of times to find fatigue limits. Any microscopic material fissure would expand rapidly under the constant high vacuum pressure differential environment. Following stress verification, we employ an advanced, continuous, non-destructive quality control protocol across all sectors. Automated crawler robots slide along the internal structural frames, firing high-energy X-ray beams. These specialized digital scanners search for tiny subsurface air bubbles trapped within thick steel components. Every single welding seam connecting the main terminal roof girders must pass this rigorous inspection. The technical data is instantly transmitted to our central database via a secure fiber network. If a single flaw is detected, a specialized laser cutting system instantly isolates the affected part.
This massive infrastructure project relies on advanced robotics. The crawler behind me is inspecting the structural integrity of these girders.
With the non-destructive inspection concluded, we advance to the massive thermal management matrix of the subterranean terminal. Operating a massive airport terminal at 350 meters depth creates extreme geothermal heat accumulation. The ambient temperature of raw bedrock at this deep level naturally reaches a scorching 45 degrees Celsius. To prevent an infrastructure thermal failure, we installed a massive closed-loop chilled water circulation network. Immense industrial chillers located on the surface continuously push freezing water through insulated vertical copper pipelines. These heavy conduits branch out into a sprawling labyrinth of radiant cooling panels embedded within ceilings. This advanced hydronic network absorbs ambient geothermal energy, stabilizing the core terminal temperature at 22 degrees. Simultaneously, we must address the intense localized kinetic heat generated by arriving and departing aircraft engines. Jet engine exhaust gases can instantly heat enclosed tunnel spaces to over 1,000 degrees Celsius. To mitigate this extreme thermal hazard, we engineered automated high-velocity water mist deluge blast systems. Specialized titanium nozzles are arrayed along the runway vaults to instantly suppress dangerous thermal energy spikes. The resulting pressurized steam is rapidly drawn out by massive multi-megawatt jet ventilation exhaust shafts. Let us observe the construction sequence of these massive ventilation shafts slicing directly up to surface. Heavy vertical blind hole boring machines grind through tough quartz layers, creating a perfect circular exhaust pathway. Subterranean engineering crew work around the clock to secure these massive vertical shafts with high-tensile steel liners. Once the ventilation infrastructure is secured, we advance to the integration of the underground aircraft taxiway guidance system. Navigating complex subterranean tunnels requires absolute spatial positioning because traditional satellite and radar signals cannot penetrate rock. To overcome this blackout, we installed a dense network of high-frequency laser radar emitters along the tunnel walls and ceilings. These specialized optical tracking arrays continuously map the tunnel interior to guide automated aircraft tugs with precision. Look closely at the heavy-duty electric towing vehicles designed to move massive aircraft without starting jet engines. This completely eliminates hazardous emissions and intense localized thermal spikes inside the passenger terminal gate areas. Next, let us observe the advanced automated aviation fuel distribution network running parallel to the taxiways. Pumping millions of liters of highly volatile jet fuel through deep underground rock layers requires absolute containment. We utilize double-walled stainless steel pipelines equipped with continuous pressurized helium leak detection monitoring systems. Any microscopic pressure drop inside the outer sleeve instantly activates automated emergency isolation valves within milliseconds. The fuel storage vaults are enclosed inside dedicated rock caverns lined with thick explosion-proof reinforced concrete jackets. Subterranean engineering crew monitor these fuel systems using rugged, spark-safe digital control consoles at the site. Let us transition to the construction sequence of the primary underground runway structural foundation slabs. To withstand the immense cyclic impact of landing wide-body aircraft, the floor requires an ultra-thick concrete layer. We employ heavy slip-form paving machinery to pour specialized steel fiber reinforced concrete blends continuously without joints. With the primary runway foundation poured, we must address the critical hydrologic drainage systems surrounding the structure. At 350 meters depth, hydrostatic pressure from deep aquifers forces water through rock fissures constantly. To handle this constant inflow, we excavated deep longitudinal drainage galleries directly beneath the runway subbase. These subterranean channels capture water, directing it toward a central high-capacity pumping station via gravity flow. Massive multi-stage centrifugal pumps made of corrosion-resistant duplex stainless steel handle thousands of liters per minute. Every single pump unit is integrated with active acoustic monitoring sensors to detect early signs of cavitation. Next, look at the integration of the automated seismic isolation bearing systems beneath the main terminal columns. Deep underground structures face intense shear stresses during tectonic shifts due to rigid confinement within bedrock matrices. To protect structural integrity, each primary support column rests on a massive lead-rubber seismic isolation bearing pad. These specialized structural dampers absorb low-frequency ground kinetic waves, preventing stress propagation into upper terminal levels. The alignment of these bearing blocks is verified continuously using high-accuracy digital hydrostatic leveling systems. Following seismic protection integration, we install the critical heavy blast doors, isolating individual terminal fire zones. These massive structural barriers are built with composite layers of dense concrete and high-tensile structural steel plates. Automated hydraulic actuators can seal these 40-ton fire barriers within 6 seconds during emergency protocols. Subterranean engineering crew systematically perform stress tests on these actuators without engaging in verbal communication. With fire containment zones established, we integrate the primary automated aircraft docking and underground passenger gate systems. The telescoping jet bridges are engineered with multi-axis magnetic sensors to align with aircraft doors completely untouched by human hands. These massive umbilical structures maintain a sealed airlock environment, preserving the positive pressure cleanroom atmosphere inside the terminal. Any seal breach would pull external rock contaminants into the pristine passenger concourse, triggering an immediate localized system shutdown. Now, observe the central command and control facility, monitoring this massive $40 billion infrastructure network 24 hours a day. A distributed industrial operating platform automatically coordinates the complex ventilation, thermal chilling, and high vacuum baggage lines synchronously. Redundant quantum-encrypted server arrays process terabytes of telemetry data per second to prevent any digital infrastructure disruptions. The entire terminal complex consumes 450 megawatts of electricity, equivalent to a medium-sized modern city. To guarantee complete energy resilience, an independent underground geothermal turbine power block operates parallel to the main grid connection. I am standing inside the core operations hub, where this immense engineering achievement is successfully brought to life. This monumental achievement shatters every traditional constraint of structural geology and advanced heavy mechanical design. We have proven that humanity can construct high-volume transportation hubs inside the most unforgiving deep crustal environments. This $40 billion masterpiece establishes a bold new benchmark for the future of six-dimensional subterranean civilization architecture. The boundaries of what was once considered impossible have been completely erased by relentless technical calculation and execution. Subscribe to TechGen Manufacturing to stay connected with the absolute edge of modern heavy engineering and megaproject fabrication.